Welcome to this peaceful journey through the cosmos, where we'll explore the mysterious and fascinating phenomena known as black holes. As you relax and prepare for sleep, let your mind drift through space and time, learning about these incredible objects that represent some of the most extreme conditions in our universe. Close your eyes, breathe deeply, and allow yourself to float through this ocean of knowledge as we gently explore the wonders of black holes. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape from inside a certain boundary called the event horizon. These cosmic objects are among the most mysterious and powerful phenomena in the universe, formed when massive stars collapse at the end of their life cycles. The term black hole was coined by physicist John Wheeler in 1967, though the concept had been theoretically predicted much earlier. The story of black holes begins with Albert Einstein's general theory of relativity, published in 1915, which described gravity not as a force, but as a curvature of spacetime caused by mass and energy. Just months after Einstein published his equations, a German physicist named Karl Schwarzschild found the first exact solution to Einstein's field equations while serving on the Russian front during World War I. Schwarzschild's solution described the gravitational field around a perfectly spherical mass, and it predicted something extraordinary. If enough mass were compressed into a small enough region, it would create a point of no return, a boundary where the escape velocity would exceed the speed of light. This boundary is now known as the event horizon, and the radius of this boundary is called the Schwarzschild radius. For an object like our Sun, the Schwarzschild radius is about 3 kilometers, meaning the Sun would have to be compressed to a ball just 6 kilometers across to become a black hole. For Earth, the Schwarzschild radius is only about 9 millimeters, smaller than a marble. The formation of black holes is intimately connected to the life cycles of stars. Stars spend most of their lives in a delicate balance between two opposing forces, the inward pull of gravity trying to collapse the star, and the outward pressure from nuclear fusion reactions in the core pushing matter outward. This balance, called hydrostatic equilibrium, keeps stars stable for millions or billions of years. Our Sun, for example, has been in this stable state for about 4.5 billion years and will continue for another 5 billion years or so. But eventually, every star runs out of nuclear fuel. What happens next depends on the star's mass. For stars like our Sun, which have relatively modest masses, the end is relatively gentle. When the Sun exhausts its hydrogen fuel, it will expand into a red giant, then shed its outer layers to form a planetary nebula, leaving behind a dense core called a white dwarf. A white dwarf is supported not by nuclear fusion, but by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. White dwarfs are incredibly dense, with masses similar to the Sun but compressed into volumes about the size of Earth. However, there's a limit to how massive a white dwarf can be. This limit, called the Chandrasekhar limit, after the Indian astrophysicist Subramanian Chandrasekhar who calculated it, is about 1.4 times the mass of our Sun. If a white dwarf exceeds this mass, perhaps by pulling matter from a companion star in a binary system, electron degeneracy pressure can no longer support it, and the star will collapse further. For stars more massive than about 8 times the mass of the Sun, the end is far more dramatic. These massive stars burn through their nuclear fuel much more quickly than smaller stars, living for only millions rather than billions of years. When a massive star exhausts its fuel, it can no longer support itself against gravity, and the core collapses catastrophically in a matter of seconds. The collapse is so rapid and violent that it generates a tremendous shockwave that blows the outer layers of the star into space in a supernova explosion. one of the most energetic events in the universe. Supernovae can briefly outshine entire galaxies, releasing more energy in a few weeks than our Sun will emit in its entire lifetime. But what happens to the core? If the core's mass is between about 1.4 and 3 times the mass of the Sun, it will collapse into a neutron star, an object so dense that protons and electrons are crushed together to form neutrons. Neutron stars are supported by neutron degeneracy pressure, similar to the electron degeneracy pressure that supports white dwarfs but even stronger. A neutron star typically has a mass of about 1.4 solar masses, but a diameter of only about 20 kilometers, making it incredibly dense. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars can spin extremely rapidly, with some rotating hundreds of times per second, and they have incredibly strong magnetic fields, trillions of times stronger than Earth's magnetic field. When we observe neutron stars that emit beams of radiation from their magnetic poles, we call them pulsars, because as the star rotates, the beam sweeps across space like a lighthouse, causing the star to appear to pulse on and off with remarkable regularity. However, if the core of the collapsing star is more massive than about 3 solar masses, not even neutron degeneracy pressure can halt the collapse. There is no known force in physics that can stop the collapse of such a massive core. The core continues to shrink, becoming smaller and smaller, denser and denser, until all of its mass is compressed into a point of infinite density called a singularity. The gravitational pull near this singularity becomes so strong that it warps spacetime to an extreme degree, creating a black hole. The boundary around the singularity from which nothing can escape is the event horizon. Once anything crosses the event horizon, it is inevitably pulled toward the singularity, never to return. This is true for matter, energy, and even light itself. This is why we call them black holes. They appear perfectly black because they emit no light. Black holes come in different sizes. The black holes formed from collapsed stars are called stellar mass black holes, and they typically range from about 3 to several dozen times the mass of the Sun. But the universe also contains much more massive black holes. Supermassive black holes, found at the centers of most large galaxies, can have masses ranging from millions to billions of times the mass of the Sun. Our own Milky Way galaxy harbors a supermassive black hole at its center called Sagittarius A star, which has a mass of about 4 million solar masses. Despite its enormous mass, Sagittarius A star is remarkably compact, with an event horizon only about 17 times larger than the Sun. Scientists believe that supermassive black holes formed in the early universe, perhaps from the direct collapse of enormous gas clouds, or through the merger of many smaller black holes over billions of years. There may also be intermediate mass black holes, with masses between stellar mass and supermassive black holes, though these are harder to detect and study. Some scientists even speculate about the possible existence of primordial black holes, tiny black holes that might have formed in the first fraction of a second after the Big Bang, though none have been definitively detected. Despite their name, black holes are not actually holes in space. They are objects with mass, and they exert gravitational pull just like any other massive object. If our Sun were suddenly replaced by a black hole of the same mass, the orbits of the planets would remain unchanged. Earth would continue to orbit at the same distance, with the same orbital period, though our planet would certainly become very cold without the Sun's warmth and light. The myth that black holes go around sucking up everything in their vicinity is not accurate. Black holes only consume matter that comes very close to them, or that happens to be on a collision course with them. At distances beyond the event horizon, black holes behave gravitationally just like any other object of equivalent mass. The event horizon is the defining feature of a black hole. It represents the point of no return, the boundary beyond which escape is impossible. For a non-rotating black hole, the event horizon is a perfect sphere with a radius equal to the Schwarzschild radius. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For a black hole with a mass of 4 million suns, like Sagittarius A star, the Schwarzschild radius is about 12 million kilometers, or about 17 times the radius of the Sun. Interestingly, the event horizon itself is not a physical surface or barrier. If you were falling toward a black hole, you wouldn't feel anything special as you crossed the event horizon. There would be no wall, no membrane, nothing to indicate that you had passed the point of no return. You would simply continue falling toward the singularity. However, an outside observer would see something very different. Due to the extreme curvature of spacetime near a black hole, time itself is affected. As you fell toward the event horizon, an outside observer would see you moving more and more slowly, your clock ticking slower and slower compared to theirs. As you approached the event horizon, you would appear to slow down asymptotically, never quite reaching it from the outside observer's perspective. Your image would also become increasingly redshifted, meaning the light from you would be stretched to longer and longer wavelengths, eventually becoming invisible. From your perspective, however, you would cross the event horizon in a finite amount of proper time. This discrepancy arises because of the different ways time flows in different gravitational fields, an effect predicted by general relativity and confirmed by many experiments. Once inside the event horizon, your fate is sealed. You would inevitably be pulled toward the singularity at the center of the black hole. As you fell, you would experience increasingly strong tidal forces. Tidal forces arise because different parts of your body would be at different distances from the singularity, and thus would experience different gravitational pulls. The part of your body closer to the singularity would be pulled more strongly than the part farther away, stretching you like taffy. Astrophysicists have a term for this process: spaghettification. For a stellar mass black hole, the tidal forces at the event horizon are so strong that any object would be torn apart immediately. However, for a supermassive black hole, the event horizon is so much larger that the tidal forces there are relatively gentle. You could actually cross the event horizon of a supermassive black hole without being immediately spaghettified, though you would eventually be torn apart as you approached the singularity. The singularity itself is one of the greatest mysteries in physics. It represents a point where our current theories break down. According to general relativity, the singularity is a point of infinite density and infinite curvature of spacetime. But physicists believe this is likely an indication that our theory is incomplete, rather than a description of physical reality. At the extreme conditions of a singularity, quantum effects become important, and we would need a theory of quantum gravity to properly describe what happens there. Such a theory would unite general relativity, which describes gravity and the large-scale structure of the universe, with quantum mechanics, which describes the behavior of matter and energy at the smallest scales. Despite decades of effort, physicists have not yet developed a complete and consistent theory of quantum gravity, though several approaches are being pursued, including string theory and loop quantum gravity. Most black holes are not perfectly spherical and non-rotating. In reality, almost all black holes rotate because they form from the collapse of rotating stars, and the conservation of angular momentum means that as the star shrinks, it spins faster, like a figure skater pulling in their arms during a spin. A rotating black hole is described by a different solution to Einstein's equations, discovered by Roy Kerr in 1963 and called the Kerr solution. A rotating black hole has several interesting properties that differ from a non-rotating one. First, it has two event horizons, an inner event horizon and an outer event horizon. Second, it has a region called the ergosphere, which lies outside the outer event horizon. In the ergosphere, spacetime itself is dragged around by the black hole's rotation, a phenomenon called frame dragging. Anything in the ergosphere, even light, is forced to move in the direction of the black hole's rotation, though it can still escape from the ergosphere if it has enough energy. The ergosphere makes it possible, in principle, to extract energy from a rotating black hole through a process called the Penrose process, named after physicist Roger Penrose. In this process, an object entering the ergosphere could split into two parts, with one part falling into the black hole and the other escaping with more energy than the original object had. This would slow down the black hole's rotation slightly, converting some of its rotational energy into the energy of the escaping particle. Some scientists have speculated that advanced civilizations might use this process to extract vast amounts of energy from rotating black holes. The rotation of a black hole also affects the shape of its event horizon, causing it to bulge at the equator and flatten at the poles, similar to how Earth is slightly oblate due to its rotation. The faster the black hole rotates, the more pronounced this effect becomes. There is a maximum rotation rate for a black hole, where the event horizon at the equator reaches the speed of light. Such a maximally rotating black hole is called an extremal Kerr black hole. For a given mass, an extremal Kerr black hole has a smaller event horizon radius than a non-rotating black hole. Black holes are not entirely black, according to a groundbreaking discovery by Stephen Hawking in 1974. Hawking showed that when you take quantum mechanics into account, black holes actually emit a faint thermal radiation, now called Hawking radiation. This radiation arises from quantum fluctuations in the vacuum of space near the event horizon. In quantum field theory, even empty space is not truly empty, but is filled with virtual particles that constantly pop into and out of existence in particle-antiparticle pairs. Normally, these pairs annihilate each other almost immediately. However, near the event horizon of a black hole, it's possible for one particle of a pair to fall into the black hole while the other escapes. From the perspective of an outside observer, it appears as if the black hole is emitting particles. The energy for these particles comes from the black hole itself, so the black hole gradually loses mass through this process. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. Stellar mass black holes have incredibly low temperatures, far colder than the cosmic microwave background radiation that fills the universe. So they are actually absorbing more energy from the background radiation than they emit through Hawking radiation, causing them to grow slightly. Supermassive black holes have even lower temperatures. However, smaller black holes would have higher temperatures, and if a black hole were small enough, it would emit significant amounts of Hawking radiation and would eventually evaporate completely in a burst of radiation. For a black hole with the mass of the Sun, the time it would take to evaporate through Hawking radiation is about 10 to the power of 67 years, vastly longer than the current age of the universe, which is about 14 billion years or about 10 to the power of 10 years. But a small primordial black hole with a mass of a mountain might evaporate in the age of the universe. The prediction of Hawking radiation leads to a famous puzzle in physics called the black hole information paradox. According to quantum mechanics, information cannot be destroyed. If you know the exact state of a system at one time, the laws of physics should allow you to calculate its state at any other time, forward or backward. However, if a black hole forms from matter and then evaporates through Hawking radiation, it seems that the information about the quantum state of the matter that formed the black hole is lost forever. Because Hawking radiation is purely thermal and contains no information about what fell into the black hole. This apparent contradiction has troubled physicists for decades. Various solutions have been proposed, including the idea that information is somehow encoded in the Hawking radiation in subtle ways we don't yet understand, or that information is stored on the event horizon in what is called the holographic principle, or that information somehow leaks out of the black hole through other quantum effects. Recent work suggests that information may be preserved through quantum entanglement between the Hawking radiation and the black hole. But the information paradox remains an active area of research and debate. Detecting black holes is challenging precisely because they are black and emit no light of their own. However, we can detect black holes indirectly through their effects on their surroundings. One way is by observing the motion of visible objects around them. If we see a star or gas cloud orbiting an invisible object at high speed, we can calculate the mass of that invisible object using Newton's or Einstein's laws of gravity. If the mass is large enough and the object is compact enough that we can rule out other possibilities like clusters of dim stars or neutron stars, we can conclude that it's likely a black hole. This method has been used to detect many stellar mass black holes in binary systems, where a normal star and a black hole orbit each other. In many such systems, the black hole pulls gas from its companion star. As this gas spirals toward the black hole, forming an accretion disk, it heats up due to friction and compression, reaching temperatures of millions of degrees and emitting intense X-rays before crossing the event horizon. We can detect these X-rays with space-based telescopes. Some of the brightest X-ray sources in the sky are stellar mass black holes accreting matter from companion stars. This same method has been used to detect supermassive black holes at the centers of galaxies. By measuring the velocities of stars and gas clouds orbiting the galactic center, astronomers can determine the mass of the central object. For our Milky Way, observations of stars orbiting the galactic center, particularly a star called S2, which has a highly elliptical orbit that brings it very close to the central object every 16 years or so, have provided strong evidence for a supermassive black hole at the center. The supermassive black hole at the center of the Milky Way, Sagittarius A star, was detected this way. Scientists tracked the orbits of stars near the galactic center for decades, and the precision of these measurements was so impressive that Andrea Ghez and Reinhard Genzel were awarded the Nobel Prize in Physics in 2020 for their work on this discovery. Another way black holes reveal their presence is through the gravitational waves they produce when they merge. When two black holes orbit each other, they emit gravitational waves, ripples in the fabric of spacetime itself that propagate outward at the speed of light. These gravitational waves carry energy away from the system, causing the two black holes to spiral closer and closer together. Eventually, they merge in a violent collision, producing a burst of gravitational waves. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves in September 2015. The signal came from the merger of two stellar mass black holes, about 30 times the mass of the Sun each, located about 1.3 billion light-years away. The collision converted about 3 solar masses worth of energy into gravitational waves in a fraction of a second, making it briefly the most powerful event in the observable universe at that moment. Since that first detection, LIGO and its partner observatory Virgo have detected dozens of black hole mergers. These detections not only confirm the existence of black holes, but also provide insights into their properties and the rates at which they merge. The discoverers of gravitational waves, Rainer Weiss, Barry Barish, and Kip Thorne, received the Nobel Prize in Physics in 2017. In 2019, scientists achieved another remarkable feat. They captured the first image of a black hole's event horizon. The Event Horizon Telescope, a global network of radio telescopes working together as a virtual Earth-sized telescope, imaged the supermassive black hole at the center of the galaxy Messier 87, located about 53 million light-years from Earth. The black hole, which has a mass of about 6.5 billion solar masses, appeared as a dark shadow surrounded by a bright ring of glowing gas. This image provided visual confirmation of the existence of event horizons and matched the predictions of general relativity with remarkable accuracy. In 2022, the Event Horizon Telescope team released an image of Sagittarius A star, the supermassive black hole at the center of our own galaxy, showing a similar structure. These images represent one of the greatest achievements in modern astrophysics. Black holes play important roles in the evolution of galaxies. The supermassive black holes at galactic centers can influence star formation throughout their host galaxies. When matter falls into a supermassive black hole and forms an accretion disk, the disk can become extremely hot and luminous, outshining all the stars in the galaxy combined. Such objects are called active galactic nuclei or quasars. The intense radiation and powerful jets of particles ejected from near the black hole can heat gas throughout the galaxy, preventing it from cooling and collapsing to form new stars. This feedback mechanism helps regulate the growth of galaxies. There appears to be a close relationship between the mass of a galaxy's supermassive black hole and the properties of the galaxy itself, particularly the mass of its central bulge of stars. This suggests that galaxies and their central black holes grow and evolve together through cosmic time. When galaxies collide and merge, their central supermassive black holes eventually sink to the center of the merged galaxy and can form a binary black hole system. These black holes orbit each other, gradually spiraling inward due to the emission of gravitational waves, until they eventually merge into a single, larger supermassive black hole. Such mergers produce the most powerful gravitational wave events in the universe. Though we have not yet detected gravitational waves from supermassive black hole mergers, because they emit gravitational waves at frequencies too low for current detectors. Future space-based gravitational wave detectors, such as the planned Laser Interferometer Space Antenna or LISA, should be able to detect these mergers. Black holes also challenge our understanding of the fundamental nature of space and time. The extreme conditions near black holes provide natural laboratories for testing general relativity in its most extreme regime. So far, general relativity has passed every test with flying colors. The orbits of stars around Sagittarius A star match the predictions of general relativity precisely. The gravitational waves detected by LIGO match the theoretical predictions for merging black holes. The images captured by the Event Horizon Telescope show exactly what we expect to see based on general relativity. However, physicists believe that at the very center of a black hole, where the singularity lies, general relativity must break down, and a quantum theory of gravity becomes necessary. Understanding what happens at the singularity remains one of the great unsolved problems in theoretical physics. Some solutions to Einstein's equations describe unusual types of black holes with even more exotic properties. For example, the equations allow for the possibility of rotating black holes with ring-shaped singularities rather than point singularities. These solutions also predict the existence of closed time-like curves near the singularity, paths through spacetime that loop back on themselves, potentially allowing for time travel. However, most physicists believe that such exotic solutions either don't exist in nature, or that quantum effects would prevent the most unusual features like time travel paradoxes. Another theoretical possibility is a traversable wormhole, a tunnel through spacetime connecting two different points in space or even two different universes. Some solutions to Einstein's equations describe wormholes, but keeping a wormhole open would require exotic matter with negative energy density. And it's unclear whether such matter can exist in sufficient quantities. Wormholes remain purely speculative at this point. Black holes have also become an important topic in the study of quantum gravity and string theory. According to string theory, the fundamental constituents of the universe are not point-like particles, but tiny, vibrating strings. String theory requires extra spatial dimensions beyond the three we experience, and it makes predictions about the properties of black holes. One remarkable result from string theory is that it can account for the entropy of black holes. Entropy is a measure of the number of microscopic states that correspond to the same macroscopic state. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that black holes have entropy proportional to the area of their event horizon, not their volume, which was surprising. String theory can explain this entropy by counting the number of different string configurations that create a black hole with a given mass and charge. And the count matches the Bekenstein-Hawking formula. This suggests that string theory might be on the right track toward a quantum theory of gravity. The study of black holes has come a long way since Karl Schwarzschild's original solution in 1916. What was once purely theoretical speculation has become observational reality. We have detected stellar mass black holes through their X-ray emissions and their effects on companion stars. We have detected supermassive black holes through the motions of stars and gas around them. We have detected merging black holes through gravitational waves. We have even imaged the shadows of black holes against glowing gas. These achievements represent the culmination of a century of theoretical work and decades of technological development. Yet mysteries remain. We still don't fully understand how supermassive black holes formed and grew so quickly in the early universe. We don't know whether intermediate mass black holes are common or rare. We haven't resolved the information paradox. We don't have a complete theory of quantum gravity that can describe what happens at the singularity. As you drift toward sleep, imagine the vastness of space, punctuated by these dark, silent objects that warp spacetime itself. Picture the stars that orbit the supermassive black hole at the center of our galaxy, their paths bent by invisible gravity. Envision the merger of two black holes, spiraling together and sending ripples through the fabric of spacetime that travel across billions of light years to reach our detectors on Earth. Think about the boundary of the event horizon, that point of no return where time and space exchange roles. Contemplate the profound mysteries that black holes represent, and the incredible human ingenuity that has allowed us to detect and study these most extreme objects in our universe. As you relax and let these thoughts wash over you, remember that the universe is full of wonders, and black holes are among the most fascinating. They remind us how much there is to learn, and how strange and beautiful the universe can be. Let yourself float through this sea of knowledge, absorbing these facts about black holes as you drift peacefully toward rest. The journey through the cosmos continues even as you sleep, and the mysteries of black holes await further exploration in your dreams. Black holes represent the triumph of mathematical prediction over intuition. When the equations of general relativity first predicted their existence, many physicists, including Einstein himself, were skeptical that such objects could really exist in nature. The idea seemed too strange, too extreme. Yet the universe has proven to be stranger than we imagined, and black holes are real. This should remind us to trust the mathematics and to be open to possibilities that seem counterintuitive. The universe does not always conform to our expectations based on everyday experience. As you continue to relax, let your mind wander through more details about these cosmic phenomena. Consider the different types of accretion disks that can form around black holes. When matter spirals toward a black hole, it doesn't fall straight in. Due to conservation of angular momentum, the matter forms a rotating disk around the black hole, similar to water spiraling down a drain but on a cosmic scale. The material in the accretion disk can be very hot, reaching temperatures of millions or even billions of degrees as it is compressed and experiences friction. At these temperatures, the disk emits intense radiation, primarily in the X-ray part of the spectrum. For stellar mass black holes, the accretion disk is relatively small, perhaps a few hundred kilometers across, but for supermassive black holes, the disk can extend for millions or even billions of kilometers. The structure of the accretion disk depends on how much matter is falling in. If the accretion rate is relatively low, the disk can be geometrically thin and cool, radiating relatively efficiently. If the accretion rate is very high, the disk becomes thick and hot, and radiation pressure from the intense radiation can even drive powerful winds that carry matter away from the black hole. In some cases, black holes can launch jets of particles traveling at nearly the speed of light, perpendicular to the accretion disk. These jets can extend for thousands or even millions of light years into space, creating enormous structures that dwarf galaxies. The exact mechanism that produces these jets is still not fully understood, but it likely involves the black hole's spin, magnetic fields in the accretion disk, and the extraction of rotational energy from the black hole itself through the Penrose process or similar mechanisms. The study of accretion disks around black holes has applications beyond astrophysics. The physics of accretion disks involves magnetohydrodynamics, the interaction of magnetic fields with conducting fluids. And this same physics appears in other contexts such as plasma physics and fusion energy research. Understanding how matter behaves in the extreme environment near a black hole helps us understand fluid dynamics in general. As you lie here peacefully, consider also the concept of tidal disruption events. Occasionally, a star wanders too close to a black hole. If the star passes within a certain distance, called the tidal disruption radius, the difference in gravitational pull on the near side and far side of the star becomes so great that it tears the star apart. About half of the stellar material is ejected at high speed, while the other half falls toward the black hole, forming an accretion disk and producing a bright flare of radiation. Astronomers have observed several such tidal disruption events, and they provide valuable information about otherwise quiescent black holes that aren't actively accreting matter. The distance at which tidal disruption occurs depends on the mass of the black hole and the size and structure of the star. For supermassive black holes, the tidal disruption radius is actually outside the event horizon, so we can observe the disruption. But for stellar mass black holes, the tidal disruption radius is inside the event horizon, so the star would cross the event horizon before being tidally disrupted, and we wouldn't see the event. Interestingly, for the most massive supermassive black holes, those with masses exceeding about 100 million solar masses, the tidal disruption radius is actually inside the event horizon, even though the black hole is huge. This means that stars can cross the event horizon of the most massive black holes without being tidally disrupted, and from the star's perspective, the tidal forces at the event horizon are actually quite gentle. Only as the star continues to fall inward toward the singularity would it eventually be torn apart. Think about the environment around a stellar mass black hole in a binary system with a normal star. If the two stars are close enough, the black hole's gravity can pull gas from the outer layers of the companion star through a point called the Lagrange point, where the gravitational pulls of the two objects balance. This transferred gas carries angular momentum and forms an accretion disk around the black hole. The disk can be turbulent and highly magnetized, with strong magnetic fields that extract angular momentum from the gas, allowing it to spiral inward. As the gas loses angular momentum and falls inward, it heats up, and the innermost part of the disk, just outside the event horizon, becomes extraordinarily hot and luminous. Some of these systems are called X-ray binaries, and they were among the first stellar mass black holes to be identified. One famous example is Cygnus X1, a bright X-ray source in the constellation Cygnus. Discovered in the 1960s, it was one of the first candidates for being a stellar mass black hole. By studying the orbit of the visible companion star, astronomers determined that the invisible companion had a mass much greater than the maximum mass for a neutron star, making it a strong black hole candidate. After decades of observations, Cygnus X1 is now confirmed to be a black hole with a mass of about 21 times the mass of the Sun, orbiting a blue supergiant star. As you relax more deeply, let yourself consider the role of black holes in the very early universe. In the first few 100 million years after the Big Bang, the first generation of stars formed from pristine hydrogen and helium gas. These first stars, called population III stars, were likely much more massive than typical stars today because the primordial gas could cool less efficiently and form larger clouds. When these massive stars died, they would have left behind black holes. Some of these early black holes may have served as seeds for the supermassive black holes we see at the centers of galaxies today. However, there's a puzzle. We observe supermassive black holes with masses of billions of solar masses in the universe when it was less than 1 billion years old. Growing a black hole from a stellar mass seed of tens of solar masses to billions of solar masses in less than 1 billion years requires very rapid growth, faster than seems easily achievable. This has led some astronomers to propose that supermassive black holes may have formed directly from the collapse of massive gas clouds in the early universe, without going through a stellar phase. These direct collapse black holes could have masses of thousands, or even hundreds of thousands of solar masses from the start, giving them a head start in growing to supermassive size. Another possibility is that dense clusters of stars in the early universe collapsed directly into intermediate mass black holes, which then merged and grew. The truth may involve some combination of these mechanisms. Observations of the earliest quasars, powered by supermassive black holes in the infant universe, provide clues about how these objects formed and grew. Future telescopes like the James Webb Space Telescope are helping to study these early black holes and to constrain theories of their formation. Let your mind drift to the concept of black hole evaporation in more detail. As we mentioned earlier, Stephen Hawking showed that black holes emit radiation due to quantum effects near the event horizon. The temperature of this radiation is inversely proportional to the black hole's mass. For a solar mass black hole, the temperature is about 1/10,000,000th of a degree above absolute zero, far colder than the cosmic microwave background, which is at about 3 degrees above absolute zero. This means that stellar mass and larger black holes are actually absorbing more energy from the cosmic microwave background than they are emitting, so they are growing, not shrinking. However, as the universe expands and cools, the cosmic microwave background will eventually become colder than even the Hawking radiation from solar mass black holes. At that point, billions of trillions of years in the future, even large black holes will begin to slowly evaporate. As a black hole loses mass through Hawking radiation, it shrinks, and as it shrinks, its temperature increases. The rate of evaporation therefore accelerates as the black hole gets smaller. In the final moments of a black hole's existence, it would be emitting an enormous amount of radiation as it rapidly evaporates, ending in a final explosion. The total time for a solar mass black hole to completely evaporate is roughly 10 to the power of 67 years. For comparison, the current age of the universe is only about 10 to the power of 10 years, so even the oldest black holes have barely begun to evaporate. A supermassive black hole with 1 billion solar masses would take 10 to the power of 94 years to evaporate. These timescales are so long as to be almost incomprehensible. If we waited long enough, far beyond the lifespan of all stars, in an era when the universe would be cold and dark, black holes would be among the last remaining objects. Eventually, even they would evaporate, leaving nothing but a diffuse sea of radiation. This far future scenario, sometimes called the black hole era, is a prediction of thermodynamics and quantum mechanics applied to cosmology. As you continue to rest peacefully, think about the paradoxes and puzzles that black holes present. The information paradox we mentioned earlier is just one example. Another puzzle involves the firewall paradox, proposed in 2012. This paradox arises from trying to reconcile three different principles. The equivalence principle from general relativity, which says that freely falling observers shouldn't experience anything special at the event horizon. Unitarity from quantum mechanics, which requires that information is preserved. And the postulate that nothing can travel faster than light. It turns out that satisfying any two of these principles seems to require violating the third. The firewall proposal suggests that there might be a violent region of high-energy particles right at the event horizon, which would violate the equivalence principle but preserve unitarity. This paradox has generated much debate among theoretical physicists, and various resolutions have been proposed, but there is no consensus yet. These paradoxes highlight the fact that we are still far from a complete understanding of black holes, especially when quantum mechanics is involved. Another fascinating aspect of black holes is the no-hair theorem, a remarkable result in general relativity that states that black holes are completely characterized by just three properties: mass, electric charge, and angular momentum. Any other information about the matter that formed the black hole, such as its composition, internal structure, or the details of how it collapsed, is lost once the event horizon forms. This is what physicists mean when they say black holes have no hair. They have no distinguishing features beyond these three numbers. Two black holes with the same mass, charge, and spin are completely identical, no matter what they formed from. This is in stark contrast to other objects in the universe. Stars, for example, can have many different properties. They can have different compositions, different internal structures, different magnetic fields, different rotation profiles. But black holes are simple. This simplicity is both elegant and mysterious. The no-hair theorem suggests that enormous amounts of information are somehow erased when matter collapses into a black hole, which connects to the information paradox we discussed earlier. The no-hair theorem has been tested observationally through studies of black hole dynamics and the gravitational waves they emit, and so far it holds up. Consider also the possibility of observing black holes with next-generation telescopes. The Event Horizon Telescope continues to improve, and future observations may be able to image the photon ring around a black hole with higher resolution, or even detect the predicted asymmetries caused by the black hole's spin. Gravitational wave detectors are also improving. Future detectors will be more sensitive, and will be able to detect black hole mergers at greater distances, giving us information about the population of black holes throughout cosmic history. Space-based detectors like LISA will open up a new frequency band, allowing us to detect merging supermassive black holes and other sources of gravitational waves that are invisible to ground-based detectors. As you relax and let these thoughts flow through your mind, imagine what it would be like to observe the universe from near a black hole. If you were in a stable orbit around a black hole, well outside the event horizon and safely away from danger, you would observe some strange effects. The light from background stars would be bent by the black hole's gravity, an effect called gravitational lensing. Stars behind the black hole would appear to be in the wrong positions, and their light would follow curved paths around the black hole. If you looked at the black hole itself, you might see a dark shadow in the center, surrounded by a ring of light from photons that are orbiting the black hole at the photon sphere, just outside the event horizon. If there were an accretion disk, you would see its light bent and distorted in complex ways. Due to relativistic beaming and Doppler shifting, the part of the disk moving toward you would appear much brighter than the part moving away. Time would also flow differently for you than for observers far from the black hole. Due to gravitational time dilation, your clock would run slower compared to clocks far from the black hole. If you spent some time in orbit around the black hole and then returned to distant space, you would find that more time had passed for distant observers than had passed for you. This is the basis for the famous thought experiment involving traveling near a black hole and returning to find that centuries have passed on Earth. A form of time travel to the future that is consistent with relativity. The closer you orbit to the event horizon, the stronger this effect would be. Near the event horizon of a supermassive black hole, you could experience minutes while years pass far away. As you sink deeper into relaxation, let's explore black holes in popular culture and their impact on our imagination. Black holes have captured the public imagination like few other scientific concepts. They appear in countless science fiction stories, movies, and TV shows. In many of these portrayals, black holes are depicted as cosmic vacuum cleaners that suck up everything around them, or as portals to other dimensions or times. While some of these depictions are purely fictional, others make a genuine attempt to portray black holes accurately. The movie Interstellar, for example, consulted with physicist Kip Thorne to create scientifically accurate visualizations of a black hole and its accretion disk. The resulting images closely match what simulations based on general relativity predict, and they help the general public visualize what a black hole might really look like. The cultural impact of black holes goes beyond entertainment. They have become a metaphor for many things: inescapable situations, regions of the internet or information spaces where data goes but doesn't come out, or even psychological states of despair or hopelessness. The very name black hole has become part of everyday language. This widespread fascination reflects the deep human curiosity about the universe and our place in it. Black holes represent both the limits of our knowledge and the power of human reason to understand even the most extreme and bizarre phenomena in nature. Think about the future of black hole research. There are many open questions that astronomers and physicists hope to answer in the coming decades. How do supermassive black holes form and grow? What is the distribution of intermediate mass black holes in the universe? Can we detect primordial black holes? And if so, could they account for some or all of the mysterious dark matter that makes up most of the matter in the universe? What happens to information that falls into a black hole? What is the correct quantum description of black hole interiors? Can we observe quantum effects from black holes? As technology improves, we will develop better tools to study black holes. Next-generation gravitational wave detectors will be able to see black hole mergers throughout the universe. Better X-ray telescopes will allow us to study accretion flows around black hole in greater detail. Continued observations with the Event Horizon Telescope and similar arrays will produce movies of black holes, showing how the gas around them changes over time. Theoretical advances in quantum gravity may finally resolve some of the paradoxes that have puzzled physicists for decades. The study of black holes also connects to other fundamental questions in physics and cosmology. For example, the relationship between black holes and thermodynamics has led to profound insights about the nature of entropy, information, and the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary surface. This idea has implications far beyond black holes and may provide clues about the fundamental nature of spacetime itself. Some physicists even speculate that our entire universe might be a kind of hologram. With the three-dimensional reality we experience emerging from information encoded on a two-dimensional surface at the edge of the observable universe. These are deep and speculative ideas, but they show how the study of black holes has led to profound questions about the nature of reality. As you continue to rest, letting these ideas wash over you like gentle waves, consider the sheer scale of black holes. The event horizon of the supermassive black hole at the center of the Milky Way, Sagittarius A star, is about 12 million kilometers in radius. This is about 17 times the radius of the Sun, yet it contains the mass of 4 million suns. If you could somehow hover at a safe distance above the event horizon and look around, you would see a vast, black sphere taking up a huge portion of the sky. The event horizons of even more massive supermassive black holes would be correspondingly larger. The black hole at the center of Messier 87, the one imaged by the Event Horizon Telescope, has a mass of about 6.5 billion solar masses and an event horizon with a radius of about 19 billion kilometers, larger than the entire orbit of Neptune around our Sun. These scales are difficult to comprehend, but they illustrate the extremes that exist in our universe. At the other end of the scale, theoretical calculations suggest that the smallest possible black holes that could exist would have masses comparable to the Planck mass, about 22 micrograms, and sizes comparable to the Planck length, about 10 to the minus 35 meters. Such tiny black holes would evaporate almost instantly due to Hawking radiation. Anything in between the Planck mass and stellar mass black holes is possible in principle, though we have only observed black holes with masses of about 3 solar masses or greater. The possible existence of smaller primordial black holes remains an open question. Let your thoughts drift now to the edges of our knowledge and the mysteries that remain. Despite all we have learned about black holes over the past century, there is still so much we don't understand. The singularity at the center remains shrouded in mystery. Our current theories predict that it is a point of infinite density, where spacetime curvature becomes infinite. But most physicists believe this is a sign that general relativity breaks down there, and that quantum gravity effects become important. What actually exists at the center of a black hole? Is there really a singularity, or does quantum mechanics prevent the formation of true singularities? Some theories suggest that quantum effects might halt the collapse before a singularity forms, leaving a region of extremely high but finite density. Others propose more exotic possibilities, such as the creation of baby universes or connections to other regions of spacetime through wormholes. Without a complete theory of quantum gravity, we cannot answer these questions definitively, and unfortunately, we cannot observe the interior of a black hole from the outside. So these questions may remain theoretical for the foreseeable future. Another mystery concerns the possible connection between black holes and the dark energy that is causing the expansion of the universe to accelerate. Some physicists have speculated about possible relationships between these phenomena, though no definitive connection has been established. Dark energy remains one of the biggest puzzles in cosmology, and black holes, as regions where spacetime is curved to its extreme, might provide clues about its nature. As you lie here in peace and comfort, absorbing these fascinating facts about black holes, let your mind wander through the cosmos. Imagine the billions of stellar-mass black holes scattered throughout the Milky Way, the remnants of massive stars that died long ago. Picture the supermassive black holes lurking at the centers of galaxies, some quietly sitting in the dark, others actively feeding on gas and shining brighter than their entire host galaxies. Envision the cosmic dance of binary black holes spiraling together, sending gravitational waves rippling through spacetime until they merge in a violent collision. Think about the extreme physics at work near black holes. Spacetime curved to its maximum, matter compressed to incredible densities. Gravitational forces strong enough to prevent even light from escaping. Consider how remarkable it is that human beings, through careful observation, mathematical reasoning, and technological ingenuity, have been able to discover and study these most extreme objects in the universe. From Einstein's equations written on paper to gravitational wave detectors kilometers long to planet-sized telescope arrays, we have built the tools necessary to explore black holes. This represents one of the great achievements of human civilization, the result of centuries of scientific progress building on the work of countless individuals. As you drift closer to sleep, let these thoughts about black holes inspire a sense of wonder and curiosity about the universe. Black holes remind us that the universe is stranger and more wonderful than we might imagine, that there are phenomena so extreme that they challenge our understanding and require us to expand our theories and concepts. They remind us that there is still so much to discover and so many mysteries to solve. The universe does not give up its secrets easily, but through persistence, creativity, and the scientific method, we can uncover truths about nature that would have seemed like magic to earlier generations. Rest now with visions of curved spacetime and event horizons, of colliding black holes sending ripples through the fabric of reality, of supermassive black holes at the hearts of galaxies, shaping the evolution of cosmic structure. Sleep peacefully, knowing that the universe is vast and full of wonders, and that the human quest to understand it continues. Dreams may take you on journeys through space and time, past event horizons into realms where our current theories reach their limits and new physics awaits discovery. The cosmos is yours to explore in sleep, and black holes are among its most mysterious and fascinating citizens. Let us continue exploring more fascinating aspects of these cosmic phenomena as you relax even more deeply. Consider the mathematical beauty of black holes and how they emerge naturally from Einstein's field equations. These equations, which can be written compactly in just a few lines using tensor notation, encode the entire theory of general relativity. They describe how matter and energy curve spacetime, and how that curved spacetime in turn affects the motion of matter and energy. The equations are nonlinear, meaning that gravity itself gravitates, unlike the simpler equations of Newtonian gravity. This nonlinearity makes the equations difficult to solve in general, but certain special cases can be solved exactly. The Schwarzschild solution for a non-rotating black hole and the Kerr solution for a rotating black hole are two such exact solutions, and they have been studied exhaustively by physicists. The elegance of these solutions has led many physicists to describe them as beautiful. Freeman Dyson once said that some equations have a quality of inevitability about them, and the equations describing black holes seem to possess this quality. When you start with Einstein's equations and look for solutions describing very compact, massive objects, black holes emerge naturally from the mathematics. As you relax and let your breathing slow, think about how black holes affect the orbits of objects around them. In Newtonian gravity, orbits are described by conic sections, ellipses, parabolas, or hyperbolas, depending on the energy of the orbiting object. In general relativity, orbits near a black hole are more complicated. The orbit of an object around a black hole will precess, meaning that the orientation of the orbit slowly rotates over time. This effect, called perihelion precession, was first observed in the orbit of Mercury around the Sun. Mercury's orbit precesses by a tiny amount that couldn't be fully explained by Newtonian gravity, and Einstein's general relativity perfectly accounted for the discrepancy. Near a black hole, where gravity is much stronger, this precession effect is much more pronounced. Stars orbiting close to Sagittarius A star show significant orbital precession, and these observations provide tests of general relativity in the strong field regime. Another interesting orbital phenomenon near black holes involves innermost stable circular orbits. In Newtonian gravity, a test particle can orbit at any distance from a massive object. But in general relativity, there is a minimum radius for a stable circular orbit around a black hole. For a non-rotating black hole, this innermost stable circular orbit has a radius of 3 times the Schwarzschild radius, or 6 times the mass of the black hole in geometrized units. Inside this radius, there are no stable circular orbits. Objects can still orbit inside this radius, but their orbits are unstable and will either spiral inward toward the event horizon or spiral outward. For a rotating black hole, the location of the innermost stable circular orbit depends on the spin of the black hole and whether the orbit is in the same direction as the black hole's rotation or opposite to it. For maximally rotating black holes with orbits in the same direction as the rotation, the innermost stable circular orbit can be as close as the event horizon itself. The innermost stable circular orbit is important for accretion disk physics, because material in the accretion disk typically spirals inward until it reaches this radius, at which point it plunges rapidly into the black hole. The emission from the accretion disk is therefore brightest in the region near the innermost stable circular orbit, and by studying the spectra of radiation from accretion disks, astronomers can infer properties of the black hole, such as its spin. As you continue to rest comfortably, let's explore black holes in the context of the universe's evolution. In the very early universe, shortly after the Big Bang, the universe was extremely hot and dense. As it expanded and cooled, structures began to form. The first stars formed a few 100 million years after the Big Bang, and some of these stars were massive enough to collapse into black holes when they died. These early black holes were the seeds of the black hole population we see today. Over billions of years, black holes have grown through accretion of gas and through mergers with other black holes. The history of black hole growth is closely tied to the history of galaxy formation and evolution. Galaxies form from the gravitational collapse of gas in the early universe, and as they grow, they undergo mergers with other galaxies. When two galaxies merge, their central black holes eventually sink to the center of the merged galaxy and form a binary system. These binary black holes orbit each other, and through various dynamical processes, they gradually lose energy and spiral inward. Eventually, when they get close enough, they emit strong gravitational waves and merge into a single black hole. This process has been repeated countless times throughout cosmic history, and it is the reason why we observe supermassive black holes in the centers of most large galaxies today. The detection of gravitational waves from merging stellar mass black holes by LIGO has opened a new window onto this cosmic history. By measuring the masses and spins of merging black holes and the rate at which these mergers occur, we can learn about the formation and evolution of stellar mass black holes throughout the universe's history. Future detectors will be able to see mergers at even greater distances, effectively looking back in time to earlier epochs of the universe. Let your mind wander now to some of the exotic possibilities that theoretical physics suggests might be associated with black holes. One such possibility is the existence of primordial black holes, which might have formed in the very first fraction of a second after the Big Bang. In the extremely early universe, before the first stars formed, the density of the universe was not perfectly uniform. There were regions that were slightly denser than average and regions that were slightly less dense. If some of these density fluctuations were large enough, they could have collapsed directly into black holes under their own gravity. These primordial black holes could have a wide range of masses, from tiny black holes with masses less than that of an asteroid up to thousands or even millions of solar masses. Primordial black holes are particularly interesting because they have been proposed as a possible explanation for dark matter, the mysterious substance that makes up about 85% of the matter in the universe, but does not emit, absorb, or reflect light. Dark matter has only been detected through its gravitational effects on visible matter and light. Various candidates have been proposed for what dark matter might be, including exotic subatomic particles that interact only weakly with ordinary matter. But another possibility is that some or all of dark matter consists of primordial black holes. These black holes would be dark and would only interact through gravity, just like the hypothesized dark matter particles. However, various observations have placed constraints on the possible masses and abundance of primordial black holes, and it now seems unlikely that they make up all of dark matter, though they might contribute to a fraction of it. Searches for primordial black holes continue through various methods, including looking for gravitational lensing effects when a primordial black hole passes in front of a background star. As you sink deeper into relaxation, consider another fascinating aspect of black holes: their role in testing fundamental physics. Black holes provide natural laboratories for testing theories in extreme conditions that we could never reproduce on Earth. For example, the strong gravitational fields near black holes allow us to test general relativity in regimes where Newtonian gravity fails completely. The detection of gravitational waves from merging black holes has allowed us to test predictions of general relativity in highly dynamical, strong-field situations. So far, general relativity has passed every test with remarkable precision. The gravitational waves detected by LIGO match the predictions of general relativity to within a fraction of a percent. The orbits of stars around Sagittarius A star match general relativity's predictions. The shadow of the black hole imaged by the Event Horizon Telescope has the size and shape predicted by general relativity. These tests are important because, while general relativity has been extremely successful, physicists expect it to be an approximation to a more fundamental theory that includes quantum mechanics. By testing general relativity in increasingly extreme conditions, we might eventually find deviations that point the way toward this more fundamental theory. Black holes are also connected to some of the deepest questions in thermodynamics and statistical mechanics. The discovery that black holes have entropy and temperature was surprising and profound. In thermodynamics, entropy is a measure of disorder, or the number of microscopic states consistent with a given macroscopic state. For ordinary objects, entropy is proportional to volume, more or less. But black hole entropy is proportional to the area of the event horizon, not the volume inside it. This suggests something deep about the nature of spacetime and information. The holographic principle, which emerged from the study of black hole thermodynamics, proposes that all the information contained in a volume of space can be encoded on the boundary of that region. Like a hologram, this principle has been applied beyond black holes and has become an important idea in theoretical physics, particularly in the study of quantum gravity and string theory. The AD-SCFT correspondence, a specific realization of the holographic principle, has provided powerful mathematical tools for studying both quantum gravity and strongly coupled quantum field theories. Think about how our understanding of black holes has evolved over time. In the early 20th century, they were purely theoretical curiosities, solutions to Einstein's equations that many physicists thought might not exist in nature. By the mid-20th century, astronomers began to realize that some objects they were observing, such as quasars and X-ray binaries, might be powered by accretion onto black holes. By the late 20th century, the evidence for black holes became increasingly strong. With measurements of stellar orbits around galactic centers and observations of X-ray emissions from binary systems. In the 21st century, black holes have moved from theoretical speculation to observational reality. The detection of gravitational waves from merging black holes and the imaging of black hole shadows have provided direct evidence for the existence of event horizons and have turned black holes into objects that we can study in detail. This progression from theory to observation is a beautiful example of how science works, with theoretical predictions eventually being confirmed by observations, sometimes decades later. As you rest here peacefully, breathing slowly and steadily, let's explore some of the practical aspects of detecting and studying black holes. Gravitational wave detectors like LIGO work by measuring incredibly tiny distortions in spacetime caused by passing gravitational waves. LIGO consists of two L-shaped detectors, one in Louisiana and one in Washington state, each with arms 4 kilometers long. A laser beam is split and sent down both arms, reflected off mirrors at the ends of the arms and recombined. When a gravitational wave passes through the detector, it causes one arm to stretch slightly while the other arm compresses slightly, changing the relative length of the arms by a tiny amount. This change in length causes the laser beams to go slightly out of phase with each other, creating an interference pattern that can be detected. The sensitivity of LIGO is extraordinary. It can detect changes in arm length that are smaller than 1/10,000th the diameter of a proton. This is equivalent to measuring the distance to the nearest star, about 4 light-years away, to within the width of a human hair. Achieving this level of sensitivity requires isolating the detectors from all sources of noise, including seismic vibrations, thermal fluctuations, and quantum fluctuations in the laser light itself. The LIGO detectors are marvels of engineering and technology, incorporating advanced laser systems, ultra-stable mirrors, sophisticated vibration isolation systems, and quantum squeezing techniques to reduce quantum noise. When a gravitational wave passes through the detectors, it creates a characteristic pattern in the data called a chirp, so named because when the gravitational wave signal is converted to sound, it sounds like a bird chirp. The frequency of the gravitational wave increases as the two black holes spiral closer together, and the amplitude increases as well until the black holes merge. After the merger, the resulting black hole vibrates like a ringing bell, producing a characteristic ringtone signal before settling into its final state. By analyzing these signals, scientists can extract information about the masses and spins of the black holes, the distance to the merger, and even test whether the merged object behaves like a black hole, predicted by general relativity. The Event Horizon Telescope, which produced the first images of black hole shadows, works on a very different principle. It uses a technique called very long baseline interferometry, where radio telescopes spread across the Earth observe the same object simultaneously. The data from all the telescopes are combined using sophisticated computer algorithms to create an image with resolution equivalent to a single telescope, the size of the Earth. This enormous effective telescope size is necessary because black holes, despite their large masses, appear very small in the sky due to their great distances from us. The black hole at the center of Messier 87 has an event horizon about 40 billion kilometers in diameter, but at a distance of 53 million light-years. It appears to have an angular size of only about 40 microarcseconds, equivalent to seeing a baseball on the moon from Earth. Creating images at this resolution requires observations at millimeter wavelengths and the combination of data from telescopes around the globe, from Hawaii to Chile to Spain to Antarctica. The resulting images show a bright ring of emission around a dark central shadow. The bright ring comes from light emitted by hot gas orbiting the black hole, with some of the light taking curved paths around the black hole before reaching us due to gravitational lensing. The dark shadow in the center is larger than the event horizon itself because it includes the photon sphere, where light can orbit the black hole. The size of the shadow depends on the mass of the black hole and is predicted by general relativity, and the observed size matches the predictions beautifully. As your body relaxes more completely and your mind drifts peacefully, consider the concept of black holes in different dimensions. In our universe, spacetime has 3 spatial dimensions and 1 time dimension, for a total of 4 dimensions. But in theoretical physics, particularly in string theory, extra spatial dimensions are often considered. How would black holes behave in universes with different numbers of dimensions? This turns out to be a rich and interesting question. In 4-dimensional spacetime like ours, the event horizon of a black hole is a 2-dimensional surface, a sphere. In 5-dimensional spacetime, the event horizon would be a 3-dimensional hypersurface, and so on. The properties of black holes change in interesting ways as you change the number of dimensions. In 3-dimensional spacetime, for example, there are no black holes in the usual sense, because gravity behaves differently in 3 dimensions. But there are objects called BTZ black holes that have some black hole properties. In higher dimensions, black holes can have more complicated shapes, not just spheres. You can have black strings, black brains, and other exotic objects. The study of black holes in higher dimensions has provided insights into quantum gravity and has revealed unexpected connections between gravitational physics and other areas of physics through the holographic principle. Let your thoughts drift to the question of what would happen if you fell into a black hole. From your perspective, if you fell feet first toward a stellar mass black hole, you would first notice tidal forces stretching you. The gravitational pull on your feet would be stronger than the pull on your head, since your feet are closer to the black hole, and this differential pull would stretch you vertically. At the same time, you would be compressed horizontally, as the gravitational field tries to pull all parts of you toward the center of the black hole. For a stellar mass black hole, these tidal forces would become lethal well before you reached the event horizon, tearing you apart in the process of spaghettification we mentioned earlier. However, for a supermassive black hole, the tidal forces at the event horizon are much weaker due to the larger size of the black hole, and you could cross the event horizon intact. Once inside the event horizon, you would inevitably fall toward the singularity. The nature of spacetime inside the event horizon is strange. In the exterior region, Outside the event horizon, time flows in the usual way, and space extends in all directions. But inside the event horizon, the roles of time and space are in some sense reversed. Moving toward the singularity becomes as inevitable as moving forward in time is in the exterior region. The singularity is not a place in space, but rather an event in your future, and there is no way to avoid reaching it, just as there is no way to avoid moving forward in time outside the black hole. As you continue toward the singularity, the tidal forces would grow stronger and stronger. Eventually, even the atoms in your body would be torn apart, and ultimately even atomic nuclei would be disrupted. What happens at the singularity itself is unknown, as this is where our theories break down. Some physicists speculate that quantum effects might prevent the formation of a true singularity, but without a theory of quantum gravity, we cannot say for sure. Fortunately, this is purely a thought experiment, as there is no reason to think anyone will be falling into a black hole anytime soon. As you lie here in comfort and peace, breathing slowly and deeply, let's think about black holes and time travel. According to general relativity, certain solutions to Einstein's equations, including some involving black holes, allow for closed time-like curves, paths through spacetime that loop back on themselves. If such paths exist, they would allow for a form of time travel to the past. However, most physicists believe that closed time-like curves either don't exist in nature, or that quantum effects would prevent them from being used for time travel. Various proposals have been made for chronology protection mechanisms that would prevent time travel paradoxes. Time travel to the future, on the other hand, is definitely possible and is even routinely achieved in particle accelerators, where particles are accelerated to speeds close to the speed of light. And due to time dilation, they experience less time than stationary clocks. Similarly, spending time near a black hole where gravitational time dilation is strong would allow you to travel to the future, as more time would pass far from the black hole than passes for you. This is not science fiction, but rather a consequence of the geometry of spacetime described by general relativity. Consider also the fate of information in a black hole from a more philosophical perspective. The idea that information might be destroyed in black holes challenges some deep principles in physics. In quantum mechanics, the evolution of physical systems is described by unitary transformations, which preserve information. If you know the complete quantum state of a system at one time, you can in principle calculate its state at any other time, past or future. The apparent destruction of information in black holes would violate this principle, suggesting either that quantum mechanics must be modified in the presence of gravity, or that the information is not actually destroyed, but is somehow preserved and eventually returned to the outside universe, perhaps through correlations in the Hawking radiation. Recent work on the information paradox suggests that information may indeed be preserved, with the key insight coming from understanding the quantum entanglement structure between the inside and outside of the black hole. The Page curve, which describes how the entropy of Hawking radiation evolves as a black hole evaporates, suggests that information begins to come out of the black hole in the Hawking radiation after about half the black hole has evaporated. Calculating this curve requires sophisticated techniques from quantum gravity and has been an active area of research in recent years. As you relax even more deeply, your breathing calm and regular, think about the role of black holes in science education and popular understanding of science. Black holes have captured the public imagination perhaps more than any other scientific concept, with the possible exception of dinosaurs. They represent the exotic and the extreme, and they have served as a gateway for many people to become interested in physics and astronomy. The visual appeal of black holes, particularly after the release of the Event Horizon Telescope images, has helped make abstract concepts in physics more concrete and relatable. Black holes also illustrate important aspects of how science works. They show how mathematics can predict the existence of phenomena that were initially hard to believe, how observations eventually confirm theoretical predictions, how interdisciplinary collaboration between theorists and experimentalists drives progress, and how technological advances enable new discoveries. The story of black holes is a story of human curiosity and ingenuity, of the power of the scientific method to reveal hidden aspects of nature. Let your mind drift to the possible applications of black holes, though admittedly most of these are more science fiction than near-term reality. Some scientists have speculated about using black hole as energy sources, extracting their rotational energy through the Penrose process, or capturing the energy released by matter falling into accretion disks. A sufficiently advanced civilization might construct a structure around a black hole to capture this energy, sometimes called a black hole engine. Black holes have also been proposed as a means of disposing of waste, though the challenges of actually transporting waste to a black hole are obviously formidable. More seriously, studying black holes helps us understand fundamental physics, and this understanding could have practical applications in the far future that we can't currently envision. Just as the development of quantum mechanics in the early 20th century seemed highly abstract and theoretical, but eventually led to practical technologies like transistors, lasers, and computer chips. As you continue to rest, absorbing these facts about black holes, let's explore a few more technical details about their physics. The Schwarzschild metric, which describes the spacetime geometry around a non-rotating black hole, can be written in different coordinate systems. The original Schwarzschild coordinates have a coordinate singularity at the event horizon, meaning that these coordinates don't work well right at the horizon, even though there's nothing physically singular there. Other coordinate systems, such as Eddington-Finkelstein coordinates or Kruskal-Shekker's coordinates, extend smoothly across the event horizon and are better for describing infalling matter. These different coordinate systems are just different ways of describing the same physical spacetime. Like how you can describe points on Earth using latitude and longitude, or using other coordinate systems. The choice of coordinates can make certain calculations easier or harder, but physical predictions don't depend on the choice of coordinates. Think about the extreme densities involved in black holes. When a stellar mass black hole forms from the collapse of a star's core, that core, which might have had a mass of several suns and a radius of thousands of kilometers, is compressed down to a region only a few kilometers across. The average density inside the event horizon becomes enormous. Though it's important to note that the matter doesn't uniformly fill the interior, but rather continues to collapse toward the singularity. For supermassive black holes, interestingly, the average density inside the event horizon can be relatively low. A black hole with 1 billion solar masses has an event horizon with a radius of about 3 billion kilometers, and the average density inside this volume is only about the density of water. This is because the Schwarzschild radius grows linearly with mass, while the volume grows as the cube of the radius, so more massive black holes have lower average densities. Of course, this doesn't mean there's water density stuff filling the black hole's interior. The matter is concentrated at or near the singularity. As you breathe slowly and steadily, feeling deeply relaxed, consider the cosmic perspective that black holes provide. They are reminders of the power and violence of the universe, the endpoints of stellar evolution for the most massive stars. They are laboratories for studying the most extreme physics, where spacetime is curved to its maximum, where quantum and gravitational effects both become important. they are also reminders of the limits of our knowledge and the mysteries that remain. Despite all we have learned, black holes still hold secrets, and studying them continues to reveal surprises and to challenge our understanding. The journey of discovery is not complete, and black holes will likely remain a source of fascination and wonder for generations to come. Let your final thoughts before sleep turn to the beauty and mystery of the cosmos. Black holes are just one of many wonders that the universe contains, from the smallest subatomic particles to the largest structures spanning billions of light years. Each phenomenon in nature, when studied carefully, reveals elegance and complexity, patterns and laws, order emerging from what might initially seem like chaos. The fact that we can understand black holes at all, that we can write equations describing them, that we can detect them across cosmic distances, is itself remarkable. It speaks to the power of human reason and the deep connections between mathematics and physical reality. As you drift off to sleep now, carry with you a sense of wonder about the universe and appreciation for the black holes that populate it, those dark sentinels scattered through space and time, shaping the evolution of galaxies and providing windows into the most fundamental aspects of reality. Sleep well, knowing that the universe is vast beyond imagining, filled with phenomena both beautiful and strange, and that black holes are among the most fascinating inhabitants of this cosmic landscape. Let your dreams take you on journeys through curved spacetime, past event horizons, through accretion disks glowing with the light of matter heated to millions of degrees. Witnessing the merger of black holes and the gravitational waves they send rippling through the cosmos. Rest peacefully in the knowledge that the universe is knowable, that through science we can understand even the most extreme and bizarre phenomena, and that there is always more to discover. Always new mysteries waiting to be solved. As you settle into deeper rest, let's explore a few more fascinating aspects of black holes that demonstrate the richness of this topic. Consider the phenomenon of gravitational redshift near black holes. Light climbing out of a gravitational field loses energy and becomes redshifted, meaning its wavelength increases and its frequency decreases. This effect is predicted by general relativity and has been confirmed by many experiments, including measurements of light from the surface of white dwarfs and the Sun. Near a black hole, gravitational redshift becomes extreme. As a photon climbs away from the event horizon, it loses more and more energy. A photon emitted from just above the event horizon will be extremely redshifted by the time it reaches a distant observer. In fact, photons emitted from exactly the event horizon would be infinitely redshifted and would take infinite time to reach a distant observer, which is another way of understanding why nothing can escape from inside the event horizon. This redshift affects observations of matter near black holes, as the light we see from hot gas near the event horizon is redshifted from its emission wavelength. Think about the stability of black holes. Once a black hole forms, it is remarkably stable. It has no internal processes that could cause it to change or decay, aside from the slow process of Hawking evaporation, which takes an enormous amount of time. Black holes are solutions to Einstein's equations that represent equilibrium states, and they are stable against small perturbations. If you perturb a black hole by throwing matter or energy into it, the black hole will briefly oscillate, emitting gravitational waves. But it will quickly settle down into a slightly larger but still stable black hole. This stability is described by black hole perturbation theory, which studies how black holes respond to small disturbances. The fact that black holes rapidly settle into stable equilibrium states is important for gravitational wave astronomy. As the ringed-on phase of a black hole merger provides a clean signal that can be used to test whether the merged object is indeed a black hole as predicted by general relativity. As you breathe deeply and slowly, your body completely at ease, let's consider the connection between black holes and neutron stars. Neutron stars and black holes are related in that both are the end states of massive star evolution, with the final mass of the stellar core determining which one forms. But there are important differences. Neutron stars have surfaces, while black holes have event horizons. Neutron stars are made of matter, albeit matter in an exotic state, while black holes are not made of anything but are instead regions of curved spacetime. The boundary between neutron star masses and black hole masses is not perfectly sharp. There's a maximum mass for a neutron star, above which neutron degeneracy pressure cannot support the star against gravity, and the star must collapse to a black hole. This maximum mass is called the Tolman-Oppenheimer-Volkoff limit and is around 2 to 3 solar masses, though the exact value depends on the equation of state of neutron star matter, which is not precisely known. Observations of neutron stars and black holes have helped constrain this limit. In recent years, gravitational wave detections have revealed mergers involving objects in the mass range, where it's unclear whether they are very massive neutron stars or low-mass black holes. And these observations are helping to refine our understanding of the boundary between neutron stars and black holes. Think about the role of magnetic fields around black holes. Although black holes themselves cannot have magnetic fields, the gas and accretion disks around black holes can be highly magnetized. These magnetic fields play a crucial role in the physics of accretion, as they can transport angular momentum outward through the disk, allowing matter to spiral inward toward the black hole. The magnetorotational instability, discovered through theoretical work and simulations, is a key mechanism for generating turbulence in accretion disks and enabling accretion. Magnetic fields also play a role in launching the relativistic jets that are observed to emanate from some black holes. The exact mechanism for jet formation is still debated, but it likely involves magnetic fields threading the accretion disk and extracting rotational energy from the black hole or the inner disk regions. These jets can extend for millions of light years and can affect the intergalactic medium, depositing energy far from the black hole itself. As you relax even further, your mind drifting peacefully, consider how black holes interact with each other. When two black holes are in a binary system, they orbit each other according to the laws of gravity. If they are far apart, they orbit according to Newtonian gravity, just like planets orbiting a star. But as they spiral closer together due to the emission of gravitational waves, relativistic effects become important. The orbits speed up, the gravitational waves become stronger and higher in frequency, and eventually the black holes merge. During the merger, the spacetime geometry becomes highly dynamical and complex. The event horizons of the two black holes merge to form a single event horizon, and the merged black hole oscillates before settling down. These oscillations, called quasi-normal modes, are like the ringing of a bell, and they depend on the mass and spin of the final black hole. By measuring the frequency and decay rate of these oscillations from gravitational wave signals, scientists can test whether the merged object is indeed a black hole and whether it behaves according to general relativity. Let your thoughts turn to the concept of black hole thermodynamics. The laws of black hole mechanics, discovered by Stephen Hawking, Jacob Bekenstein, and others in the 1970s, bear a striking resemblance to the laws of thermodynamics. The first law of black hole mechanics relates changes in the black hole's mass to changes in its area, angular momentum, and electric charge. Similar to how the first law of thermodynamics relates changes in energy to changes in entropy and other state variables. The second law states that the total area of black hole event horizons never decreases in any process, similar to how entropy never decreases in thermodynamic processes. The analogy becomes even more striking when one includes Hawking radiation, at which point it becomes clear that black holes actually have temperature and entropy. Not just analogies to temperature and entropy. The temperature of a black hole is inversely proportional to its mass, and the entropy is proportional to the area of its event horizon. These relationships have deep implications for our understanding of the nature of spacetime and information. As you drift closer to sleep, your breathing slow and rhythmic. Think about the observational techniques used to study black holes in different wavelengths of light. X-ray observations have been crucial for detecting stellar mass black holes in binary systems, as the hot accretion disks emit strongly in X-rays. Radio observations have been important for studying jets from black holes, and for the very long baseline interferometry that enabled the Event Horizon Telescope images. Infrared observations can penetrate dust that obscures optical light, allowing astronomers to observe regions near black holes that would otherwise be hidden. Optical observations have been crucial for measuring the velocities of stars orbiting supermassive black holes. Gamma-ray observations can detect the most energetic processes near black holes. Multi-wavelength observations, combining data from different parts of the electromagnetic spectrum, provide the most complete picture of black holes and their environments. Future missions will continue to push the boundaries of what we can observe, with more sensitive X-ray telescopes, improved radio telescope arrays, and new space-based observatories. Consider the possibility of intermediate-mass black holes, which would fill the gap between stellar-mass black holes and supermassive black holes. These black holes, if they exist, would have masses from hundreds to hundreds of thousands of times the mass of the Sun. There have been some candidate observations of intermediate-mass black holes, including in globular clusters and ultraluminous X-ray sources in other galaxies. But confirmed detections have been elusive. Understanding whether intermediate-mass black holes are common, rare, or non-existent would help us understand how supermassive black holes form and grow. Some of the black hole mergers detected by LIGO have resulted in final black holes with masses in the lower end of the intermediate mass range, providing indirect evidence that such black holes can exist, at least as the products of mergers. Think about the cosmic microwave background, the afterglow of the Big Bang, and how black holes affect it. When the cosmic microwave background photons pass near clusters of galaxies that contain supermassive black holes, they can be scattered and gain energy, an effect called the Sunyaev-Zeldovich effect. This effect has been used to study clusters of galaxies and the black holes within them. The presence of black holes in the early universe also affects the ionization history of the universe, as the energetic radiation from accreting black holes can ionize hydrogen gas, contributing to the reionization of the universe that occurred a few 100 million years after the Big Bang. As you lie here in complete relaxation, your body still and peaceful, let's explore how black holes connect to other areas of physics and mathematics. The study of black holes has inspired developments in differential geometry, the mathematics of curved spaces, as understanding black hole spacetimes requires sophisticated geometric techniques. Black holes have also influenced developments in quantum field theory, as Hawking radiation arises from quantum field theory in curved spacetime. String theory has benefited greatly from the study of black holes, with black hole entropy calculations providing key tests of string theory's validity. The AD-SCFT correspondence, one of the most important developments in theoretical physics in recent decades, emerged from thinking about black holes in anti-de Sitter space and their relationship to quantum field theories. This correspondence has applications far beyond black holes, including in condensed matter physics and the study of quark-gluon plasmas. Consider also the philosophical implications of black holes. They challenge our intuitions about causality, determinism, and the nature of information. The fact that events inside the event horizon cannot influence events outside raises questions about the nature of physical laws and whether they apply universally. The information paradox forces us to question whether information is truly fundamental and inviolable. Black holes also raise questions about the nature of singularities and whether physics allows for true infinities or whether quantum effects always regulate potentially infinite quantities. These questions touch on deep issues in the philosophy of science and the nature of physical law. As your mind becomes quieter and more peaceful, ready for sleep, think about how black holes have influenced popular culture beyond science fiction. They have appeared in music, art, and literature as metaphors and symbols. The visual imagery of black holes, especially after the Event Horizon Telescope images, has inspired artists and designers. The concepts associated with black holes, such as event horizons, singularities, and spacetime curvature, have entered the broader cultural vocabulary and are used to discuss topics far beyond astrophysics. This cultural impact reflects the deep human fascination with the extreme and the unknown, and black holes serve as a perfect embodiment of both. Let your final thoughts turn to the future of black hole research. In the coming years and decades, we will continue to make new discoveries about black holes. Gravitational wave detectors will become more sensitive and will detect more mergers, including mergers of supermassive black holes once space-based detectors like LISA are operational. The Event Horizon Telescope will produce higher-resolution images and eventually movies showing how the gas around black holes changes over time. New telescopes across the electromagnetic spectrum will provide more detailed observations of black holes and their effects on their surroundings. Theoretical developments may finally resolve the information paradox and other puzzles, perhaps through a complete theory of quantum gravity. We may discover new types of black holes or new phenomena associated with black holes that we haven't yet predicted. The study of black holes will continue to be at the frontier of physics and astronomy, pushing the boundaries of our knowledge and understanding. As you settle into sleep now, let all these thoughts about black holes gently fade into the background of your consciousness. Know that you have learned about one of the most fascinating phenomena in the universe, objects that represent the extremes of gravity, density, and spacetime curvature. Black holes are the remnants of dead stars, the hearts of galaxies, and the sources of some of the most powerful events in the cosmos. They are regions where our current theories reach their limits and where the mysteries of quantum gravity await resolution. They are laboratories for testing general relativity and windows into the fundamental nature of spacetime and information. They are objects that were once thought to be impossible, but are now known to be real and abundant throughout the universe. Rest now, with a sense of wonder and appreciation for the beauty and strangeness of the universe. Let your dreams carry you through the cosmos, past stars and galaxies, past event horizons into the unknown, exploring realms where space and time intertwine in ways that challenge our everyday understanding. Sleep peacefully, knowing that the universe is full of wonders waiting to be discovered, that human curiosity and ingenuity will continue to unveil its secrets, and that black holes will remain among the most captivating subjects of scientific inquiry for generations to come. Drift now into restful sleep, your mind filled with images of curved spacetime, of gravitational waves rippling through the cosmos, of bright accretion disks surrounding dark event horizons, of colliding black holes releasing more energy in a fraction of a second than the sun will emit in its entire lifetime. Sleep well knowing that somewhere in the vast expanse of space, black holes are silently warping the fabric of reality, drawing in matter and energy, growing and evolving over cosmic timescales, waiting to reveal more of their secrets to future generations of scientists who will continue this grand adventure of understanding the universe we inhabit. Good night, and may your rest be as deep and peaceful as the quiet darkness at the heart of a black hole, where time stands still and the universe reveals its most profound mysteries. As you close your eyes for the final time tonight, let yourself feel gratitude for the gift of curiosity, for the ability to wonder about the universe and to understand it through science. Black holes remind us that the universe is far stranger and more wonderful than we might have imagined, that nature operates according to mathematical laws that we can discover and understand, and that there is beauty in the extreme and the exotic. They teach us humility, showing us how small we are in the cosmic scale, yet they also demonstrate the power of human intelligence, showing us that even the most distant and extreme phenomena can be studied, understood, and appreciated. Think of all the scientists, engineers, and thinkers who have contributed to our understanding of black holes over the past century. From Einstein, who wrote the equations, to Schwarzschild, who found the first black hole solution, to Chandrasekhar, who calculated the mass limit for white dwarfs, to Oppenheimer, who studied stellar collapse, to Penrose, who proved singularity theorems, to Hawking and Bekenstein, who uncovered black hole thermodynamics, to the thousands of astronomers who have observed black holes and their effects too. The engineers who built LIGO and the Event Horizon Telescope, to the theorists working today on quantum gravity and the information paradox. Each person has added a piece to our understanding, building on the work of those who came before, and the quest continues. As you drift into the deepest sleep, let the majesty of the cosmos fill your dreams. Imagine standing on a planet orbiting a distant star, looking up at the night sky, and seeing the bright glow of an accretion disk around a black hole. A sight no human has ever witnessed, but one that may exist somewhere in the universe. Picture the dance of binary black holes as they spiral together, their gravitational embrace drawing them ever closer until they merge in a flash of gravitational waves. Envision the supermassive black hole at the center of our galaxy, patient and silent, occasionally consuming wisps of gas that venture too close. Sitting at the heart of the Milky Way, as it has for billions of years. The cosmos is vast and beautiful, full of wonders beyond counting, and black holes are among its most magnificent creations. Rest well and good night.